Hello, I'm Dan, and today I'm going to talk about binary search in Swift. We will start to define what binary search is, why it is used, and a step-by-step example and a demo code. Binary search is a search algorithm that allows us to search any element from a collection of items and return the index of the given search. Binary search works repeatedly, dividing in half the array that could contain the target value. It compares the target value to the middle element and determines whether to continue the search to the left or to the right side from the ordered array. Note that the collection needs to be in ascending order when using binary search. We will start by a simple array. In this case, we would like to find the index of the item 1. Let's get the mid value first and compare it with a given search. To do this, we need a low index, high index, so that we can calculate the middle index. And with the middle index, we have the middle value. Then we ask if the given search is equal to the middle value. If not, we need to ask if the search value is in the left side or the right side from the middle index of the array. We will move the indices according to the result of these questions. In this case, we should move the high index to the left side of the middle index. We calculate the middle index from the low and high indices, get the middle value, and ask the same questions again. Because the middle value is the same as the search value, then we have found our index, which is 0, and we should return it. So how fast is binary search? Instead of timing intervals, we should focus on the worst case scenario detected by the big O notation. Big O notation is a simple form of communicating how fast an algorithm is. We could formulate this by checking the steps taken related to the number of items we had in the array. In this case, we can say that the number of steps taken is the log base 2 of 5. But in big O notation, we don't take the number of items, and we simplify it by replacing the number of items with an n. In this image, I present possible ways we can represent how fast an algorithm is. Notice that the O log n is the fastest representation, and n factorial is the slowest. Now, I will present how to do binary search in code. Okay, so here we have an enum with a static binary search function that we'll use in order to implement our binary search. Below, we have one test with several samples that will guide our implementation. Let's start by implementing the first sample. In this case, we are expecting the algorithm to deliver the index 2 when searching for the item of value 5. If we run it, Command U, we get a fatal error, and this is because we haven't implemented anything yet. Let's fix this by making the test pass. Let's run it. We have made the test pass because we are returning the expected value of 2. Let's commit and move on. Delivers the middle index when searching for the middle value. Great. Let's uncomment the second sample. In this case, we want to search the value of 1 and we're expecting the index 0 as a result. We run the test with Command U. The test fails, saying it's expecting optional 0 but got optional 2. Let's fix this. We know that we must return 2 when the given search value is 5. That means that we need to get the middle value. To do this, we must first find the middle index using the lowest index and the highest index of the array. Let low index, which is the start index of the list, high index, which is the end index. End index is 1 greater than the last valid value of the array, so we need to subtract 1 to it. Last list index before the end index. Let's get the middle index by adding the low and high index together and dividing it by 2. Mid index is a low index plus the high index divided by 2. This is because we would like to have an even number at all times. Then we can take the value of the middle index. Net value list mid index. We check if the middle value is the same from the search item. If it is, then we return index 2. And if it is not, then we return 0 to make the test pass. So the search item is equal to the mid value, then we return 2. If it's not, just return 0 to make the test pass. Command U, the test pass, and we are able to commit. Delivers first index 1, searching for the first value. Great. Let's uncomment the next sample. Command U. In this case, we're expecting index 4 when searching for the item value 9. The tests say that the expected value is optional 4, but we got optional 0 instead, when we are searching for the value item of 9. Let's make the test pass again. So we know that the last value will be always greater than the middle value. Let's check if the search item is greater than the middle value and return the expected index. Else if the search item is greater than the middle value, then we should return the expected index, which is 4. Command U. Perfect. The test passes. Let's commit. Delivers last index 1, searching for the last value. Great. That's not the whole story. Now we need to test the edge cases. Let's uncomment the next sample and run the test. In this case, the test failed because we are searching one item less than the first item in the array. So we know that the test is failing because we are falling back to the else when the search item is less than the middle value. We should iterate this process until reaching the first index of the array. We can achieve this by moving the high index to the left side of the middle index and iterating until reaching the first index of the array. We will use a while loop that iterates the array, but we know that we should stop until reaching the first element of the array. So we should iterate the array while the low index is less than or equal to the high index. While low index is equal or less than the high index. While the low index is less than the high index, then we get the middle value through the middle index and ask the questions again. If the search item is less than the middle value, then we should move the high index 1 value less than the middle index. We will return 0 because we need to iterate the array until reaching the first value of the array. We need to make the compiler happy by making the high index a variable. And we should return nil if the search item is not found. In or none. Let's run the test. The test failed, saying that it is expecting the index 0 when searching for an item value of 1, but got 2 instead. This is because the algorithm is returning 2 when comparing the middle value to the search item, which is 1. Let's fix this by returning the middle index instead. Let's run the test. Nice, it passes. Let's commit. Delivers none when searching one value less than the first value. Perfect. 2 more to go. Let's uncomment the next sample and run the test. In this case, we are searching for the value 10 and expecting none as its index, but we're getting optional 4 instead. Let's fix this. So we see that we return 4 when the search item is greater than the middle value, but we need to keep searching until reaching the last value. We will move the low index to the right side of the middle index first and iterate it until reaching the last value of the array. Let's delete the returning of the value 4 first. Then we move the low index to the right side of the middle index. Low index is the middle index plus 1. We make the compiler happy by changing the constant low index to a variable and run the test. Fantastic, it passes. Let's commit. Delivers none when searching one more than the last value. Perfect. Now let's uncomment the last sample. In this case, we will expect to return none when a value is not included in the array, but it's inside the array's bounds. And run the test. It passes. This is because we have made the algorithm to keep searching until reaching either the first value or the last value of the collection. Let's commit. Delivers none on an item value that's not inside the array, but inside the boundaries of the array. Nice. We have made our binary search algorithm. Thanks for watching, and I'll see you next time.